All right. So this is going to be the recording for Lab 5, the Standard Candles Lab. I'm redoing this recording because I'm an idiot and forgot to hit the record button during the actual lab. So I'm just going to be going through the lab itself, talking about the background material and also the procedure, and kind of walk you through some of the details on how to do the measurements, and hopefully help you with some misconceptions that you might run into. So this lab, the purpose of this lab is, if you recall the last lab, we did parallax, which is we were measuring the distance to stars using this parallactic shift. So we took an observation of an object in the sky from one location, say on one side of the Earth, went to the other side of the Earth, or at the same time we were on one side of the Earth and we were on two sides of the Earth at the same time, took a picture of that star, let's say, or if you remember, we did an asteroid, and we'll see a shift based on parallax. And using that and some trigonometry, we can calculate the distance to that object. But that technique breaks down. If you remember, that was actually a question in the last lab. Um, when and why does parallax break down? And we can't really use parallax out to a distance of about, I think it was 500 parsecs. And the reason for that is because the parallactic angle that we're measuring at that object is going to be way too small for us to have the ability to measure it. So once we get out past 500 parsecs, we need a new technique in order to measure distances to objects. And that's what this lab is all about. That's what standard candles are. So before we jump into that distance measurement, first we need to start talking about the idea of magnitudes. So magnitudes of objects in space, it's really, the magnitude of an object is just a measurement of its brightness. So here we're talking about, initially, we're talking about apparent magnitude. That is, there are going to be two distinctions in this lab. We have apparent magnitude and we also have absolute magnitude. They're similar but different. Apparent magnitude is going to be how bright a star in the sky appears to us. So if I'm looking through a telescope at a star in the sky, it'll look like it's a certain brightness, but that brightness may not be how bright the star actually is. You can think of it this way. If I have a light bulb, and let's say it's a 60-watt light bulb, and I'm holding it right here in front of my face, then it's going to look like a 60-watt light bulb. But if I give the light bulb to my friend, and my friend runs it to the other end of a football field, and I'm looking at that light bulb now that it's 100 yards away, then it will appear dimmer than it actually is. It will appear to me as if it's maybe like a 40 or 30-watt light bulb, right? So the light bulb, it's actually a 60-watt light bulb. That is its true brightness. That is what we call the absolute magnitude. But to me, when I'm looking at it and it's at the other end of the football field, I'm going to see it as a 30-watt light bulb because it's so far away. So the idea behind this distance measurement is, if I know how bright the object is supposed to be, how bright it actually is, the 60 watts, and I can measure how bright it appears to me, that'd be the 30 watts, then I can do math and calculate the distance to that object. So that's what magnitudes are. It's, again, just brightness, but it's actually a little bit of a weird measurement. It takes some getting used to. The brighter an object is, actually the more negative its magnitude becomes. And if an object is very faint and dim and not very bright at all, then its magnitude is very positive. The reason for that is because I think, I'm not quite sure, but I believe magnitude of 0 was chosen to be the star Vega a long time ago, just as a starting reference point, and eventually we found stars that are, of course, much brighter than that and dimmer than that, so we had to dance around a magnitude of 0. Also, it's not incredibly important for this lab, but the magnitude scale is actually what we call a log scale. So the difference between a magnitude of 2 and a magnitude of 3, that doesn't mean that the magnitude 2 star is one less brighter than the magnitude 3 star. Um, it's probably more like 5 times brighter or dimmer, whichever way. But again, that's not super important for our purposes right now. For our purposes, all you need to think about is that magnitude is the brightness of a star. And the important thing is to differentiate between absolute magnitude and apparent magnitude. So for this first part of the lab, and I will point out, just to be sure that you don't miss it, this is the first part of the background section that I'm looking at, and there are questions that you need to answer within this section. So just be careful of that. So the first part of this section is talking about how we measure the brightness. Let's say we're interested in star A here in this image. We want to measure how bright that star appears to us. So I could measure it right now as is, and I would get a certain brightness, let's say 10. But that may not be true to the true value of the star, because there could be clouds in the way. There could be other things wrong with my telescope. So we want to use a reference star, like you see here in this image, and this is used to calibrate the image, essentially. So we also measure the brightness of a reference star, which we know has which we know the apparent brightness of. And you can see that down here in the questions. It asks you to measure the magnitude of the reference star, and then it tells you the known true magnitude of this reference star is 12.01. So then you are able to get a correction constant from this. So let's say I measured my reference star to be 10 magnitudes, but the problem here is telling me that the actual magnitude of that reference star is 12.01, then I would get a correction constant of 2.01. So then I go and measure the brightness of star A, and I add on that correction factor. So let's say I measure star A to have a magnitude of 5, then the actual measured magnitude should be 5 plus the correction factor of 2.01. And so you're going to do that. It's not a hard process for that first background section. The only thing that I need to point out is how you actually measure these brightnesses. And to do that, I'm going to switch over to Afterglow. And for this whole lab, we're going to be using sample images. So in Afterglow, you're going to go to Sample Images, Astro 101, Standard Candles, and then you're going to go to this CD47 and open the image. And here you want to make sure that you're choosing the correct stars. So you're going to compare this image to the one that's in the lab, because in the lab it has those stars labeled for you. So if I go back here, I can see that there's a galaxy down here in the bottom right. That's what that smudge is. So that will kind of help give me a reference and figure out where I am in my image. But in general, to measure the brightness of any object in an image, you can use this tool in the top left right next to the ruler. It's the blue circle with a red circle inside it. If you click on that, it'll bring up a table, and then you can hover over a dot, one of the stars, and then click on it, and it will tell me the magnitude, the brightness of that star. So here it's telling me that star has I'm measuring a magnitude of 12.83, right? So that's how you do that first background section. All we're doing there is learning about magnitudes, brightnesses, and how to calibrate our images. So, like I said before, now that we understand magnitudes, we can actually start worrying about calculating the distance to these stars, because we need a new technique in order to get past that 500 parsec cutoff where parallax doesn't work anymore. So the point here is, remember, like what we just did in the background section there, we measure an apparent magnitude of a star. And if I know what its absolute magnitude is, how bright it actually is, if I was like on the surface of that star, how bright would it appear? That's the absolute magnitude. If I have those two values, the apparent magnitude and the absolute magnitude, then I can calculate the distance to that star. And that's what this equation is telling you here. D is the distance that you're solving for. And we denote magnitudes with the letter M. The lowercase m is going to be your apparent magnitude, and then the capital M is your absolute magnitude. So just be careful not to mix those up. So when you're measuring these things in Afterglow, it'll provide you with a brightness in magnitudes, and you plug those in here, and it will spit out a distance with units of kiloparsecs. So the trick here, we can take a picture of the sky and measure brightnesses like I just did in Afterglow, and that'll give me this lowercase m, right? That's the apparent magnitude. But how the heck do I know what the capital M is? How do I know the absolute magnitude of a star? And to do that, we have these special stars called standard candles. Standard candles are special because every single of this type of star, we know what their absolute magnitudes are. There are three types of standard candles that we're going to be using in this lab. We're going to be using RR Lyrae stars, Cepheid variable stars, and type 1a supernova. So the first type of standard candle is this RR Lyrae star, and it's special because it's a variable star. Its brightness varies over time, kind of like what this graph is showing here. It gets brighter and dimmer and brighter and dimmer over the course of a very special period. It's a continuous period. So the reason for the variability of this brightness is because the star heats up the outer layers of gas, so the photosphere of the star. And if you've had any experience with thermodynamics, you know that as gas heats up, it expands. So that photosphere, as it heats up, will expand and become more transparent or less opaque to the light that is coming out of the center of the star. So light is able to get through now, and it'll start cooling off because there's no more energy. So the photosphere will start cooling back down, which means it condenses back down and becomes opaque to the light that's in the inside again. The light can't get out as easily anymore. So it goes through that expanding and contracting cycle, and that causes the variability in the brightness. But it's not important for you to know that. It's just a cool little factoid. So these RR Lyrae stars, like I said, they get brighter and dimmer over a very specific period. For the RR Lyrae stars, their period is almost always going to be about less than a day, around half a day, something like that. They're really not going to get more than a day long in their period. And from that, so if I look at a star and I measure its brightness over the course of a couple days maybe, and I plot out the brightness, then I can see it has this period. And If I see the period is less than a day, let's say, then I can be like, all right, that tells me this is an RR Lyrae star, so I know what the absolute magnitude is. And the absolute magnitude of all RR Lyrae stars is going to be this 0.75. That's my capital M. So then, once I have that, I can go back to this equation here for distance, and I can plug in my measured magnitude, and then I can plug in that 0.75 for my capital M, and that'll give me the distance to that RR Lyrae star. So that's what you're going to be doing for the first section, and I'll go into more detail in a little bit. For the next section, for the second section of the lab, you're going to be doing the same thing, but for a different type of star. This is still a variable star, so it gets brighter and dimmer as time goes on. These Cepheid variable stars, the only difference is that their periods are longer. So unlike the RR Lyrae star, which had a period of about a day or less, these Cepheid variable stars, their periods can be pretty long. They can be on the order of days, sometimes even months. And to get the absolute magnitude of a Cepheid variable star, it's a little bit more complicated. And that's what this plot is trying to show you here. So again, this y-axis here is just brightness, and the x-axis is time, it's days. So you can see here this blue line is the RR Lyraes. So the period for RR Lyraes, again, only extends out to about 1 day. So no matter how many RR Lyraes I measure, I get, a range of periods. This star may have a period of 0.5, this star may have a period of 0.7 days. All of those RR Lyrae stars are going to have a absolute magnitude of 0.75. For Cepheid variable stars, it's a little different. Their absolute magnitude that I measure, or that I calculate, it depends on the period of their variability. So let's say I look at a star, I measure its brightness over a couple of days, and it looks something like this, and I say, okay, the period is longer than a day. So that tells me it's a Cepheid variable star. So I take that period and I go down to this plot. Let's say I found the period was 7 days. So I'll go to about here, and then that tells me, if I go to the corresponding point on the y-axis, that will tell me what the absolute magnitude is. And that is what this equation is showing you here. So this is how you calculate the absolute magnitude of a Cepheid variable star. You measure the period of that variability, and you plug that in here. That's what P is. And you want it to be in units of days, and it'll spit out the absolute magnitude. Then, again, you can go back up to this distance equation, plug in your magnitudes, your apparent and absolute magnitudes, and then you can calculate the distance to that Cepheid variable star. The last standard candle that we're going to be using is the type 1a supernova. And you've probably heard about supernovas before. They're stars that explode, right? So this is a little different than the first two stars that we talked about. It's no longer a variable star that gets brighter and dimmer and brighter and dimmer. In this case, it's an explosion in space. So the star blows up, it gets really bright really fast, and then all the energy and matter is going to dissipate out into space. So it's going to get dimmer as time goes on. It's never going to get brighter again. And that's what this plot is showing you here. This is just brightness versus time of the supernova. And you can see that it peaks initially and then slowly dies off in brightness as time goes on. So what we can do is we can look at a star, measure its brightness over time, and if we see its light curve, that's what this is called, if we see its light curve peak up like this and then die off, then we can tell ourselves, okay, that is a supernova. I know what the absolute magnitude of a supernova is. And for type 1a supernova, the absolute magnitude is going to be this negative 19.3 value. So those are the three types of standard candles we're going to be using. So to keep this lab kind of structured in your head, there are three sections. You're going to be calculating the distance to an RR Lyrae star, to a Cepheid star, and to a type 1a supernova. Each one has its own little caveats, but that's the general idea of this lab. So let us jump right into that. The first part of the procedure, like I said, is you're going to be measuring the distance to an RR Lyrae star. So if you recall, back in the background section here, in order to measure the distance to that star, we need the absolute magnitude, and we get the absolute magnitude by looking at the period of the variability. So let me go back down here to the procedure. I want y'all to be using this NGC 1261. This is a globular cluster, and in here the stars are RA labeled for you, and so that you can go find them. For example, for my demonstration, I'm going to be using this 3201 globular cluster. Don't use this one. This is just purely to show you how to do it, because I don't want to be giving away all the values and answers when I'm doing it for this one. But I want you to use this NGC 1261 globular cluster when you're doing this. So, and also make sure you answer in this section which one you're actually using. So again, we want to be making that light curve, right? The brightness versus time, and you'll see it getting brighter and dimmer. So we need to be measuring these brightnesses. So again, I'm going to be using this one. If I go to Afterglow, let me get rid of this. What I want is to use this process called batch photometer. And essentially what this is, it's similar to the tool we were using in the background, this blue and red circle here. It's measuring the brightness, but it allows me to do it for a bunch of images at once. That's the only difference. So it's going to look similar to the aligned feature we've used in the past. I'm just going to load in the images that I want to use. Remember, I'm using this 3201 cluster. You will be using 1261 here. So I'm going to load those images in. And it should look something like this. So it's going to pull up all of my images and show them on the left here. Make sure you have the Stellar PSF method selected. And what I want to be doing is I want to tell this tool which stars I'm concerned with. So if I go back to the lab, I'm going to be using this image as my reference. So it may take a little practice getting used to finding all the patterns in this image, in your image. But what you want to do is you want to identify which of these dots is your RR Lyrae star. That's what the RRL stands for. And which one of these dots is your reference star. Remember that reference star is being used in order to calibrate our images. The key thing here is this image in the lab and this image in Afterglow. It's possible they could be flipped compared to one another or rotated compared to one another. So you have to be careful with that, because if you pick the wrong or incorrect stars in this image and carry through the process, it's really going to screw up all your data. So take your time on this. I'm going to look back at the lab And near my stars that I'm concerned with, I see a little chunk of stars here that kind of looks like an L, maybe. So that's a pretty strong feature that I'll look for. And then over here, I'm seeing these three big bright stars here that also kind of form an L. So I'm going to look for those in my image and see if they match up. And again, this will take some time. I've already done this one, so I know where they are. It helps to look for bright stars in your image. So remember I had that bright L, but I actually have that bright L here on the left-hand side now. So that means my image is actually flipped compared to the one in the lab. So I can fix that by just using the orientation tools up here at the top. Just for my purposes, I'm flipping it. So now it should match what is in the lab. So I have my bright L here. And then if I go over here, I have that small cluster right there. So now I can look back at the lab and figure out which stars are which. So this is my RR Lyrae star. So now I want to tell this tool which stars are which. So you can start that by just clicking on the star, and it will bring up a little label on the star. I'm too zoomed out to see it right now, but you get inside the tool, you can actually name the label. So I'm going to change that name to RRL, telling me that it's my RR Lyrae star. And then I'm going to click on the star that is my reference star, which is this one here. And again, I'm going to rename it here. I'm going to call it ref. Then the next thing is we've told the tool where these two stars are in this first image. And the nice thing about this tool is we can use this find sources in all images button, and it'll apply that to all the images, and it'll find those two stars in every single image. The only trick here is that we want to use this WCS instead of this pixel XY. All that means is that these images have data stored inside them. It's called a FITS header. And all that is, it's just, it has data stored regarding the position of these stars on the sky, rather than the XY coordinate, pixel coordinates in the image. That may not make a whole lot of sense right now, but not super important. Just make sure you're using this WCS option. Otherwise it won't work. So now you can use this find sources in all images. I'll click on that. And now when I go through and click on any of my other images, it'll have found those two stars. In this case, they're in the bottom right, but it still successfully found them in this image. In this case, my image was rotated compared to the original one. If I click on another image, same thing, it still found them, but it was rotated. For this image, they're back up in the top left, but it still successfully found them. So my two stars are labeled in every single one of my images. So now I can hit next, and it will bring up this big table. All this table is telling you is the brightness for those two stars in each image. And that's what this magnitude column here is on the right. So, for example, I have my RRL star, my variable star. It has a magnitude of 14.42 in image 1. And then my reference star has brightness of 13.6 in image 1. And then the next line is image 2 for my variable, and image 2 for my reference, image 3, image 3, image 4, image 4, and so on. But we aren't really going to be using this table specifically. We're going to be plotting this, and this tool is actually super useful because it automatically plots for you. If you go to Export, Data Analyzer, and then Variable Source, click on it, it'll bring up this plotting tool for you. And it's going to look really messy at first. That's because we need to tell the tool some things. So the first thing we need to tell it is which of those two stars that we labeled is the star that we care about, the RR Lyrae star. That's what this variable source is. So I'm going to tell it my variable source is the RRL, and then my reference source is going to be my reference star. And remember, the whole point of the reference star is to calibrate our image. So we need to tell this tool what the actual magnitude of my reference star is. That's what this box is here, and that value is given to you in the lab. For my cluster, it's 13.6. So that's what I'm going to put in there. 13.6. Cool. So now the whole idea here, remember, is that we're trying to figure out what the period is of that variability for our star. Right now, this data doesn't look that great. This is the y-axis is brightness and the x-axis is time in days. And it doesn't look like that continuous sine curve, right? It's pretty messy, and there are multiple reasons for that. It could be that our data is noisy due to bad measurements, and also it could be that our data wasn't taken at the same time every day. It wasn't evenly sampled, is what we would say. So we're going to use this technique called period folding. And there is a video in the lab in this section here, tutorial on period folding. I highly suggest you go watch that video because it has some good visuals that help explain what period folding is and why it works. But the idea behind it is we give the tool an initial guess of what we think the period may be of this star, and then it will plot what it thinks that should look like, and then we can kind of iterate and clean it up a bit. So that's what this is here. You want to check the period folding box and enter in what you think the period may be. Right now it's set to like 8.6. That's going to be completely wrong. The problem here is I have no idea where to start for my initial guess. I could guess 20 days, I could guess 3 days. I don't know where to start. So to help out with that, we're going to use this Fourier view option. We are currently in the light curve view. That's what the default is when this plotter opens up. But we want to switch to this Fourier view. So I'm going to click on that. I'm going to get rid of the period folding. And you can see there's already some sort of trend here. The idea behind Fourier view, Fourier was a French guy, mathematician, and there's this thing called the Fourier transform. And I'm not going to get into the details of it because it's some complicated math. For our purposes, just imagine it as a black box where you stick in the values for these settings and it spits out an answer that's useful. Okay, there's some pretty complicated math behind Fourier transforms. Don't worry about it too much right now. All you're doing here is you're in the Fourier view and you're going to be entering in some settings that the lab tells you you need. So if I go back to the lab, in this section, it says in the Fourier view, I'm going to be using a start period of 0.3 days, stop period of 1 day, and a step size of 0.001 days. So now I go back to Afterglow and enter in those numbers. Start of 0.3, stop of 1, and a step size of 0.001. Cool, and it should look something like this for yours. There's going to be a very large peak in your plot. What we're concerned about here is the highest peak on the plot, and that for me is this one here. Remember, this x-axis is the period in days. So you can see that this highest peak has a period of about 0.55 days. And I can actually hover over these data points and it will tell me the exact X and Y coordinates of that point. So you can see here in these boxes, it gives me 0.558, 5569, somewhere around there. So that's going to be my initial guess for this light curve period folding that we're going to use. So I know the period should be around 0.558-ish. So now I'm equipped with that initial guess, and I go back to the light curve view, and now I want to use period folding. So I'm going to click on the box. I'm going to enter in that 0.558 number. So that's my initial guess. It may not be the perfect one yet. To double check that, remember I want my light curve to look something like increasing in brightness and then drop in brightness and then increase again. It's not going to be a perfect sine wave, but it should look similar. So I have 0.558 right now. That doesn't look too terrible. I can see how the data may rise up and then fall again. But I can play around with it. I can try 0.557, for example, and that'll change it up a little bit. Maybe 556. It's getting a little bit more scattered now, so I'll go back to 8, maybe 559. So that's what you're doing here, is you're iterating over these, trying out different ones, and seeing which one looks best. And I think for the globular cluster that I told you to use, it'll look prettier than this one. So play around with it a bit. It shouldn't change much from the initial guess, but double check, because sometimes it could be a little off. But here it looks like that initial guess is pretty accurate, as best as it's going to get. So I'm going to use that 558 number. Let me try 557. Yeah, not much of a change. So 0.558 is probably pretty close. So that is the period of my variable star. And that tells me immediately what kind of star it is. If you remember, going back to the background section, the period of a RR Lyrae star is going to be less than a day. And we found that our period was 0.558 days. So that tells me immediately that it is an RR Lyrae star, which means that its absolute magnitude is 0.75. So I can come back down here. I enter in the period that I found, which would be 0.558 days. That tells me that it is definitely an RR Lyrae star, and that tells me that the absolute magnitude is 0.75. And if you remember that distance equation, it had the little m and the capital M. We just found capital M, so now we need the little m, which is the apparent magnitude. It's the magnitude that we're measuring and how it appears to us. To get that from the light curve that we just made, you're going to just assume the halfway point between a peak and a trough on that variability. So if I go back to my light curve, you can kind of visualize that the curve will go up like this. The peak is probably around here, and then it dies off again, right? So I would say that my halfway point is probably sitting around 14 magnitudes. So that's going to be my apparent brightness that I would enter in here. That's my little m. And then I have everything I need to go and calculate the distance to that RR Lyrae star using this equation here. And that's the big idea for the process. The next section, you're doing basically the exact same thing, but for a Cepheid variable star. And remember, those have a period of longer than a day, sometimes a couple of days, sometimes a month even, or a couple months. But you're going to be going through the same process. And you should find a longer period that'll tell you what the absolute magnitude is. Remember, though, that for a Cepheid variable star, the absolute magnitude is not the same for all Cepheids. You have to, once you find the period of your Cepheid variable star, then you go back and use this equation to figure out what the absolute magnitude of your Cepheid is. And then, again, you're going to take the halfway point of your light curve to get the apparent magnitude, and then you will be able to calculate the distance to that Cepheid variable star. The final section is now for a supernova. Remember, supernova explosion, it's going to get really bright and then die off. It's not going to be this variable light curve that we've done for the past two sections. So it's going to be a little different. Also, there's a small caveat for this section. You have to make a movie. If you remember in the last lab for the asteroid, we had to make a movie of a bunch of images in order to identify which of the dots in that image was the asteroid, because the asteroid was moving across the field of view. In our case, just looking at this picture here, we don't know exactly which dot our supernova is. I'll tell you right now, it's not this smudge here. That's actually a galaxy. So it's going to be a dot. So what a supernova, what we expect it to look like is, remember, it's going to be bright and then it's going to kind of fade away to nothing. So when we make our movie, we should see one of these dots just slowly disappear to nothing. And that tells us that that dot is our supernova. So you've made movies in the past in this lab, so you should be pretty good at it by now. Remember, first you need to align all of the images, and then you can make your movie with those aligned images. We have a reference star here again for the photometry. You can use that for the alignment if you want. And I would suggest using maybe this star up here for the alignment as well. Probably not the best idea to use the galaxy as the alignment star. So make your movie, align your images, make your movie, and identify which of those dots is your supernova. And like the past labs, upload your movie to the lab if you can. You're gonna probably have to take a video with your phone. That's fine. Crop it to make it smaller so you can upload it. If you have trouble with that, you can always email it to me as well. So you upload your movie. So once you know which of those dots is your supernova, you're going to be doing the same thing in Afterglow, where you're going to be using the batch photometer. Process, batch photometer, and you're going to load in the supernova, which is the Lab 5 Standard Candles Faraway Galaxy. Faraway Galaxy 2765. This one here. You're going to load in all those images, and then you will again tell it which one your reference star is, make sure you label it, which one your supernova is, label it, and then you'll be able to go through that plotting process again. And in this case, we're not finding a period because it's a supernova. All we're doing is we're showing that it is a type 1a supernova, because remember, their light curves are going to peak up and then die off. So we're going to see the light curve, and we're going to be like, all right, that is a supernova. That tells me that the absolute magnitude is, if I go back to the background section, the absolute magnitude of my star is negative 19.3. And then the lab tells us that the apparent magnitude of my supernova is going to be the peak of that light curve. We're not using the halfway point anymore for this one. We're going to be using the peak brightness of that light curve. That's for our little m. And then, same thing as usual, we plug those two values into our distance equation and calculate the distance. And that's it for the lab. So again, to keep it structured in your head, you have first section is the R.R. Lyry variable star, where you're finding the period of that variability. You get the absolute magnitude. You have the apparent magnitude, which is that halfway point. You calculate the distance. Next section, exact same thing for the Cepheid variable star, finding the period and the halfway point for the apparent magnitude. But remember, to get the absolute magnitude, you actually have to plug that period into an equation. And then you can calculate the distance. And then the last section is the supernova. First, you have to make a movie to figure out which dot the supernova is, and then you can measure the brightness and get that light curve. And I know what the absolute magnitude of a supernova is. And then for the apparent magnitude, I'm using the peak of that light curve. And that should do it for Lab 5. So if you have any questions, definitely email me and I will be happy to help. So stay safe, wash your hands, and I'll see everyone next week.